So in this video we're going to find the eigenvalues and eigenvectors for a 3 by 3 matrix. And it turns out that when you are looking for the eigenvalues and eigenvectors of a matrix, the larger the dimension of the matrix, the more tedious the hand calculation will become, because you need to calculate by hand the determinant of an increasingly large matrix. So what we're going to want to use from 2 homeworks ago is the properties of determinants. And in particular, we want to use property 3, where we said that if we obtain a matrix B from A by adding a scalar multiple of a row or column to another row or column, then the resulting matrix B has the same determinant as the original matrix A. So we'll want to use property 3 when we get to the point where we need to calculate a determinant in order to induce zeros into the determinant calculation. So I went ahead and worked this out ahead of time, and then I typed it up. It was a long calculation, so I thought it would be easier if I typed it for you to be able to follow along with the work. So the calculation of the eigenvalues and eigenvectors for a 3 by 3 matrix, the work process or workflow is going to go the same way that it did in the 2 by 2 matrix example. We want to find the eigenvector, and the eigenvector has to be a vector that has the property that the matrix A times that vector is equal to a scalar times that vector. And then our job is to figure out what that scalar is and then use the scalar to determine the eigenvectors. So I'm going to go ahead and replace the A with my matrix A, and then we put the identity matrix, 3 by 3 matrix, in here. Multiplying by the identity matrix won't change the value of the right hand side. It is the matrix equivalent of multiplying by 1 in the real numbers. So, and the reason for doing this was to get 2 matrices of the same size so that this subtraction in this step will work, because subtraction requires that we have matrices of the same dimension. So we set this up, we distribute the lambda into the matrix, which will put lambdas on the main diagonal. And we then, once we do that, we subtract this from both sides and then factor the x out front. So we did a subtraction, we distributed lambda, did the subtraction from both sides, and used the distributive property for matrices to pull the vector x, the eigenvector we're looking for, out into the front position, or to the right. We then do the subtraction, and because everywhere except the main diagonal has zeros in the subtraction, everything stays the same except for the main diagonal, where you get 5 minus lambda, 5 minus lambda, and 2 minus lambda. So the only thing that changes is that main diagonal. And once we get it in position, we recognize that in this step we have a homogeneous system of equations, which means that the trivial solution, the zero vector, exists. And what we want is eigenvectors need to be non-zero. By definition, they are non-zero vectors. So if the zero vector exists, then the only way we can get non-zero vectors x that are solutions to this system is to have infinitely many solutions. And to do that, we need this matrix here to not have an inverse. We need this to be a non-invertible matrix. So for that to happen, this matrix needs to be singular. In other words, its determinant must be equal to 0. We remember from the last homework that if the determinant of a matrix is 0, the inverse of the matrix doesn't exist. So we wind up having infinitely many solutions if we have a homogeneous system. So we step down and say, hey, we need to calculate the determinant of this matrix, but we want to make sure that the matrix is equal to 0. Notice it's not a vector, because a determinant is just a number. So this really is a shift in process. Here I was getting myself set up so I know what the coefficient matrix is that I'm working with. I then shift gears to say, hey, I want the determinant of this coefficient matrix to be 0, so the inverse of it doesn't exist, which then guarantees infinitely many solutions or non-trivial solutions. And right here, the calculation of this determinant would really start to be a pain in the butt. Because let's say you expand it with respect to row 1. Well, what's going to happen? You're going to get 5 minus lambda. And remember, the cofactors go in a plus minus plus pattern. So it'd be 5 minus lambda times this matrix. And then we would have minus 4 times the matrix that contained these terms plus 2 times the matrix that contained these terms. And that calculation and the simplification and factorization of the resulting polynomial would be difficult. So the idea is to try to introduce zeros into the matrix using property 3 of the determinants, because if we can introduce zeros using property 3, we're guaranteed that the resulting matrix has the same determinant value as the original matrix. So here what I noticed is that if I took the opposite of row 2 and added it to row 1, I could get a 0 in this position, because the opposite of 2 is negative 2 plus 2 is 0. The opposite of the opposite of 5 minus lambda would be negative 5 plus 4 is negative 1, and it would be the opposite of the negative would give me a plus lambda sitting there. And then negative 4 plus 5 is 1, so I wind up with 1 minus lambda. That introduces a 0 into this position. And then I want to notice that these two terms are opposite of each other. So if I added this to this, I would get 0. So once I see that, I say, hey, I'm going to take the opposite of column 1. I'm going to add it to column 2 and replace column 2 with the result. So we do 1 minus lambda plus minus 1 plus lambda is 0. 4, it should be, we're just adding. It shouldn't be an opposite. There's a typo right there. Just column 1 plus column 2. 1 plus negative 1 plus negative lambda plus positive lambda gives you the 0. Then you go 4 plus 5 minus lambda is 9 minus lambda. And then we do 2 plus 2 and get the 4. So this determinant has the same value as this. And now we've introduced 0 into 2 positions, which is going to make the calculation of the determinant much simpler, because if I expand now with respect to row 1, I only need to worry about this first term because the other terms will 0 out. So calculating this determinant, I do 1, it goes to plus minus plus pattern, so it's plus or positive 1 minus lambda times the determinant that you get when you strike out row 1, column 1, which is going to be 9 minus lambda, 4, 2, and 2 minus lambda right here. 9 minus lambda, 4, 2, and 2 minus lambda. And now this is just a 2 by 2 matrix, so we know to take the determinant of the 2 by 2 matrix, we take the product of the diagonal elements. So right here is the product of the diagonal elements minus the 8 that we get by taking the product of the other diagonal elements. I don't want to fuss with multiplying this into that parentheses because this is already in a factored form. So we want to focus the simplification on the inside of this parentheses. So multiplying this out and simplifying by combining like terms yields the second degree polynomial lambda squared minus 11 lambda plus 10. And then this is going to factor as lambda minus 1 times lambda minus 10, which you can verify by multiplying this out, would verify that we get back the previous result. So as before, the other thing we want to recognize is that this polynomial that we get out of this calculation, this polynomial here, is the characteristic polynomial, just like it was for 2 by 2 matrices. Really, we're trying to find the characteristic polynomial and then find its zeros. And when we look at this, we see that we have a repeated 0 because when you plug in lambda equal to 1, both of these factors will 0 out. So we have 1 repeated 0, and then 10 it will 0 this factor out. So our eigenvalues are 1 and 10. So this is just the eigenvalue calculation. So the next slide, once we find the eigenvalues, we need to then move forward and find the eigenvectors that go with each eigenvalue. So for the eigenvalue of 1, remember that we're just trying to find non-trivial solutions to this system right here. So I need to take that system, and then I need to plug my eigenvalue into the system. So I do 5 minus 1 is 4, 5 minus 1 is 4, and 2 minus 1 is 1. And really now I'm just solving this homogeneous system of equations. And going back to like one of the first homework assignments, we know that we could just construct the augmented matrix. The augmented matrix is just going to have the 0 vector down here, so you could almost do the calculation without it. I put it in just because I like to put it in. I think it's helpful. So anyways, you put the matrix in as an augmented matrix. You then put that matrix into reduced row echelon form. Hopefully you can see that this row is a scalar multiple of this one, or these two rows are scalar multiples of this one. So it'd be easy to zero each of these rows out and then divide this row here by 2. So 1/2 of row 3 would give you 1, 1, 1/2. And then you could interchange row 3 and row 1 to get the reduced row echelon form. Alternatively, if you couldn't see it by eyeballing it, you could put it into GeoGebra. You know how to put a matrix into reduced row echelon form in GeoGebra. So you could do it by hand or with the computer algebra system. At this point of the semester, unless you're specifically told to put a matrix into reduced row echelon form by hand, you can always assume that it's okay to do it with the computer algebra system. And then we just need to interpret the result. So this we know says x sub 1 plus x sub 2 plus 1/2 x sub 3 equals 0, because this is an augmented matrix. So we extract that information from the matrix. We then solve for x sub 1 by subtracting x sub 2 and 1/2 of x sub 3 from both sides, which gives us this. And just like we've done before, we then take what's left, the variables on the right hand side, and we assign them to names. So we say let x sub 2 be r and let x sub 3 be t. So we'll give them new variable names, and we recognize that r and t can be any real number that you want. And once we do that, we construct the eigenvector right here, the eigenvector, right? This is the guy we're looking for. What's the eigenvector? So the eigenvector x sub 1, x sub 2, x sub 3 is going to equal, we replace the x sub 2 and x sub 3 with the r and the t from this step here, and then put that result into the x sub 1 position, and then x sub 2 is equal to r, so r goes in that position, and x sub 3 is t, so I've got t down in the x sub 3 position. And notice you can break this eigenvector right here. This is the eigenvector that goes with lambda equals 1. You can break this eigenvector up in a summation in terms of the r and t pieces. So if you distribute the r in and the t in and then add the result, you can verify for yourself that you get this back. This would be the more common way to do it. Again, we haven't talked about vector spaces yet, but we are going to talk about vector spaces soon, and eigenspaces. And what we're going to learn is that these two vectors are a basis for the eigenspace generated by the eigenvalue of 1. And then you have to walk through the same process for your other eigenvalue. Lambda equals 10 is a second eigenvalue. We have the system we're trying to solve so that we can find the eigenvector x that goes with the eigenvalue of 10. So we put 10 in for lambda. We do the subtractions. 5 minus 10 is negative 5, 5 minus 10 is negative 5, and 2 minus 10 is negative 8. And once we get the system here, we can put it into the augmented matrix, the same that we did here. In this case, I was lazy and I put this into GeoGebra, and I put it into reduced to row echelon form in GeoGebra. And then once it's in that form, we just interpret the result. X sub 1 minus x sub 3 equals 0. That's right here. Solve it for x sub 1. X sub 1 equals 2x sub 3. The second row says x sub 2 minus 2x sub 3 equals 0. So there it is. Solve it for x sub 2. And then we see that x sub 3 is the variable that controls each of x sub 1 and x sub 2. Give x sub 3 a name. I used x sub 3 equal u to use the different letters than I had used for lambda equal 1. U can be any real number you want, and then put your eigenvector into vector form. X sub 1 is going to equal replacing x sub 3 with u, so we'll get 2u. We replace x sub 3 with u, so x sub 2 is 2u, and x sub 3 we assign the variable name u. And notice that the u could be factored out front. This eigenvector right here forms an eigenspace that corresponds to lambda equal 10. And what you'll learn in a future video is that this vector is a basis for the eigenspace. Anyways, that's how you calculate the determinant of a 3x3 matrix. Again, as you can see, the calculation for the 3x3 matrix was much more intensive than the calculations were for the 2x2 matrix. And it would be utterly evil to ask a person on an exam to find the eigenvectors and eigenspaces for a 4x4 or 5x5 matrix. We would use a computer algebra system to find the eigenvalues and eigenvectors at that point.